Okay, good evening, everybody. Let's start our today's discussion on medicinal chemistry. Today, we will mainly focus on the problem which are described in assignment 4. We will see how to solve these problems. Okay, so let's start. Can you see my screen?
Yes, sir.
Okay. Okay, so our first problem is you have already done this assignment, right? Already submitted. You have this assignment, right?
Yes, sir.
Okay. Okay, so what is there in the question? Which of the following terms best describes the intrinsic ability of a drug to bind to a receptor? A 16-year-old girl suffering from seasonal ri- rhinitis shared a therapy with lortine, a drug that binds to H1 histamine receptor. So, what is the answer? Is this affinity or potency or efficacy or intrinsic activity? Okay, so let's first discuss about what is receptor and what is drug. So anybody wants to say anything that what is receptor? Broadly, any broad idea, not very accurate definition I am asking for. What is receptor? We have already discussed about it in our previous classes.
So can I?
Yes, sure.
So, like in basic terms, receptor is a protein on the surface of cell, which
Hmm.
which has a role for binding to various substrates.
Hmm.
And when
Substrate.
substrate binds with
Yes.
receptor,
Hmm.
it
Hmm.
produces some effect.
Some effects on our living body, right?
Yes, sir.
It activates or deactivates some pathway and biological process takes place, right?
Yes.
Okay, so yes, you are right that receptor is any cellular macromolecule that a neurotransmitter or a drug binds to initiate its effects. The endogenous function of a receptor is to participate in neurotransmitter or psychologic regulation. Drugs can be given to activate or block these receptors to produce a variety of effects, right? So yes, receptors are widely available. They are surface proteins. They can bind with some biologically active molecule and produce some effect, some good effects on some, or some adverse effect on the physiological system of our body, right? So now next question is what is drug? Anybody?
So like it is a we can say it is a xenobiotic, which is a basic like chemical moiety,
Hmm. Hmm.
which
Exactly. This is a chemical substance.
yes, sir.
Yes, absolutely right. You are. The drug is a chemical substance that interacts with a receptor to produce a psychologic effect. The ability to bind to a receptor is mediated by the chemical structure of the drug that allows it to interact with the complementary surface of the receptor. So, drug is designed in such a way that it binds, like this is the receptor. Now drug is designed in such a way that it had some chemical functionalities in it that it can interact with the receptor and can bind with the receptor, right? So now the next thing comes that all drugs are chemicals, but not all chemicals are the drug. This is very much true that all chemicals not have such kind of specific functionality to interact with the receptor. For a drug to produce a psychologic effect, it must first bind to a receptor. Two factors related to the chemical nature of a drug determine the interaction of the drug with receptor and hence the effect a drug will have on the psychologic process. Okay, so now let's take an example that what we can say a drug. Can you name this molecule? What is the name of this molecule? This is a very known and very important molecule in our body.
So dopamine.
Dopamine.
Yes, exactly, dopamine. And what is the function of dopamine? It is a basically what? And can you
Sir,
know this molecule? Second one.
sir, it can like it is a basic biogenic amine which we say, which acts
Yes.
on adrenergic receptors.
This one, you are talking
Yes,
about
sir.
dopamine. Yes. This is a neurotransmitter, right? It carries the impulse of the neuron and it processes the signal. This is a very important neurotransmitter, dopamine. So it activates dopamine 1, 2 receptors, and it also activates alpha 1 adrenergic receptor. On the other hand, this molecule, which is called, this has a name, amphetamine. Okay, so as we know that dopamine has a very important role in our body, but this molecule, can you see, though it looks same like dopamine, it also has two carbon atom and then a primary amine group and a aromatic benzene ring is present in it, but it does not activate any receptor directly. So we can see that though these molecules, two molecules are very similar, they looks like very similarity, but there are some functional groups are there, maybe due to this OH group or any functionality, it can activate a certain receptors and it cannot. So we can say that all these drugs are chemicals, but all chemicals are not drug. It should bind with the certain receptor to activate it, right? To bind a receptor, the functional groups on the drug must interact complementarily surface of the receptor. Okay, so if suppose this is the concentration of drug and this is the concentration of the receptor. So this is a reversible reaction between these two. Sorry, this is one and this is reverse reaction of the rate constant of the reverse reaction, and we are getting a receptor drug complex. Okay, so now we can define another constant kd, which is defined as the k inverse 1 by k1. Okay, so the amount bound to the receptor, amount of the drug bound to receptor is given by sorry, due to some technical issues, this is given by d by d plus kd. Okay, so the amount of the drug bound to receptor is given by this expression, amount of the drug by amount of the drug plus kd. What is kd? Kd is the another constant which is given by k inverse 1, that is the rate constant of the reverse reaction, divided by k1, that is the rate constant of the forward reaction. So the amount drug bound to the receptor is dependent on the drug concentration and kd. So now we will come to our original question, that what is our right answer then of this question?
Sir, affinity.
Affinity. Yes. So can you tell me what is potency?
Sir, potency is defined as like a dose of drug which produces some biological effect.
Potency is a measure of the amount of a drug required to produce a defined biological effect. Okay, the measure of the drug, measure of the amount. Okay. Okay. Measure of the amount is potency. And efficacy, what is efficacy?
Sir, it is a measure.
Effectiveness.
Yes, please. Anybody saying anything? Please continue.
So it can also be referred as effectiveness.
It is a measure of maximum biological effect resulting from a drug binding to its target. Okay, measure of maximum biologic effect. Okay, and intrinsic activity.
Sir, it is same as affinity.
Intrinsic activity is a measure of the ability of a drug is bound to the receptor to generate an activating stimulus and produce a change in the cellular activity. Okay, so our right answer is the affinity. Affinity is a measure of the tightness with which a drug binds to a receptor. Okay, so it is clear to everybody.
Yes, sir.
Anybody has any doubt? Anybody?
No, sir.
Okay, then we will move to our next question. Okay, so please ignore this mark on the screen. It have came due to the touchpad. Can you see my screen now? It is not creating a much problem.
Yes, sir.
Okay, so please ignore this mark. Okay, so in our next question, it is asking, then an agonist contains a alcohol, amine, and aromatic ring of which act as the binding group. Which of the following modification is most likely to result as antagonist? So, how we will answer it? Anybody wants to say anything?
Sir, it can be possible by adding some heavy groups,
Heavy groups, like other than these groups, what is mentioned here, or these
sir,
groups?
like aromatic ring and benzene ring.
Okay, okay. We will see it. Okay, an alcohol, what is the functionality of an alcohol? This one, right? Then it also have some amine group in it, right? And it also have some aromatic ring. So the what is the structure of aromatic ring? Common structure, a benzene ring, or substituted benzene ring, or polyphenolic ring, right? Okay, so it is saying that these groups are present on these molecules and it acts as the binding groups to the receptor. So at first you tell me what is agonist and what is antagonist. What is agonist?
Sir, agonist is a, like we can say, it is very similar to endogenous substrate,
Hmm?
which binds with the receptor,
Hmm?
same like endogenous substrate binds with
Hmm?
it, and
Hmm?
it produces the same effect which endogenous substrate produces.
Uh, it activates the receptor, right?
Yes, sir.
It activates and receptor, and the antagonist is just opposite to the agonist,
Agonist.
right? Uh, So it helps to deactivate the receptor. Okay, so both of agonist and antagonist both have to bind to the receptor first. This is very important. If a antagonist doesn't bind to the receptor, then it cannot exert its effect on the receptor, right? So in order to for a drug to be antagonist, it must bind effectively to the binding site. Okay, this is very important, that whether a compound is agonist or an antagonist, it has to bind to the active site of the receptor, but causes a different induced fit such that the receptor is not activated, right? So antagonist first bind to the receptor, then it changes some conformational, exerts some effect on the receptor, that there is some conformational change in the receptor, so it cannot show its actual effect due to the presence of this antagonist molecule. Okay, so now adding an extra aromatic ring to the structure is the modification that is most likely to succeed if the ring interacts with the extra binding region within the binding site. Okay, so as it is mentioned here that aromatic ring which is present at the binding site of the agonist which binds with the receptor, so we can add a more number of the ring at that various site, then it will bind to the receptor and exert the opposite effect than the agonist. Okay, so all the other modifications suggested are likely to disrupt the binding of the binding groups already present resulting in a weak agonist or an inactive compound. Yes, anybody wants to say anything?
Hello, sir.
Yes.
Agonist means is it a part of drug or a whole drug?
No, it can act as a whole drug. Means the nature of the drug we are telling that it is, or it is activating the receptor, or it is if it is acting in a negative way, then we are calling it antagonist.
Suppose that we have taken, I mean, a paracetamol.
Hmm.
So, is it agonist or antagonist? How to identify?
No, there, that we cannot say like this. It is depending on the pathway on the receptor. Then we have to do the pathway study in which pathway it is acting the receptor. It is a complete cellular biology things. That is, we cannot say like this. It is agonist or antagonist. This case is depending on the which receptor it is
Hmm.
interacting with. Okay,
Okay,
if
okay.
it activates the receptor, then it is agonist,
Hmm.
and if it
Okay,
blocks the receptor or deactivates the receptor, then it is antagonist. There are various receptors are works in a very complex biological process. There are various biological pathways are there, various enzymes are involved in this process. So then we have to do a detailed study of that with very hectic work. So we are not going in that much complication. We are just saying that if it is activating the receptor, then it is agonist, and if it is working as a blocker of that receptor, then it is antagonist, just opposite of
okay,
the agonist.
okay, okay,
Okay, so is it
okay,
clear to everybody that why we are adding a more number of the aromatic ring to the structure, so it can bind to the receptor and exert the opposite effect of the agonist. Like other there are other options we should consider, that converting the alcohol to a methyl ether, that if a alcohol is there, alcohol is OH, we are converting it to the methyl ether, that is OMe. So it is definitely not binding at the active site. Okay, so OH has some definite groups. It may react with the hydrogen bonding. Suppose it may forms with the hydrogen bonding with the compounds groups present in the receptor. So when we are changing this oxygen with the methyl group, then definitely it is not forming any bonding activity with the receptor. So it will not bind to the receptor. So definitely this option cannot work, right? Synthesizing an analog which lacks the aromatic ring. So the bonding connectivity is due to the aromatic ring. So if we delete the aromatic ring from the structure, then it will not bind to the receptor. And converting an amine to amide. So an amine is given, and we are converting it the amide NHCOR. So definitely it will not work because the bonding connectivity is due to the NH2, and when we are converting this amine to the amide, then it will not going to work, not going to bind with the receptor, right? So our right answer is adding an extra aromatic ring to the structure. Okay, any doubt anybody, or we will move to our next question?
No, sir.
Okay, then we are going to our next question. Okay, which of the following compounds is achiral? Okay, so at first you tell me what is chiral and what is achiral things. Then we will answer this question.
Sir, chiral compounds are optically active. Uh,
Yes,
they
chiral
will
compounds
rotate
are
the plane
optically active.
polarized light.
Yes, absolutely. They will rotate the plane polarized light in a certain direction.
Yes, sir.
Okay, anything? Anybody wants to add anything in this regard? Please, anybody wants to say anything different from this?
A carbon with four different groups.
Yes. carbon with four different groups is said to be optically active compound. Okay, so let's see. Yes, everybody is right. So chirality is the property of the molecule, any molecule, which tells us whether this particular atom or group in chiral environment or not. Okay, so the molecule which is not superimposable on their mirror image are called the chiral molecule. So definitely somebody says that it rotates the plane polarized light in a certain direction. So it is, then we will call it optically active or the chiral compound, right? So let's take an example of the one group is present here. Okay, so can you name this compound? What is the common name of this compound? Very common.
It's a lactic acid.
Yes, lactic acid. Very good. Okay, so if we see that the four bonding of this central carbon atom are four different groups, right? So this compound is optically active or inactive,
It's an optical active.
or it is chiral or achiral?
Chiral.
Chiral molecule. So if we place a plane, mirror plane over here, then we will, if we take the mirror image of this molecule, is these two compounds are superimposable? This is the
No,
mirror
sir.
image of this molecule. No, right? If suppose if this compound rotates the right in the this direction, then this compound will rotate right in the opposite direction, right? So this compounds is chiral and optically active, as it is non-superimposable mirror image of each other. Okay, so it so this is optically active compound. So a test for the achirality is the presence of a mirror plane within the molecule. If a molecule has a mirror plane within it that will cut it into two symmetrical halves, then it is achiral. Therefore, lack of such plane indicates the molecule is chiral. Compounds that contain a single stereocenter are always chiral. This compound, like example, it has this simple stereocenters, and this is always chiral molecule. Okay, so you got understood that what is the optically active and optically inactive compound, what is chirality.
Yes, sir.
And another, with chirality, another term comes along with the chirality. What is that? Stereogenicity. You know what is stereogenic center? What is the criteria of stereogenic center? Chirality and stereogenicity, these two terms come very in a very similar way, but they are different. Definitely, they have the different from each other. Anybody say what is the stereogenicity, how we determined it? Then we will discuss why these two terms are different. Anybody? How we check the stereogenicity of a center? Okay.
Sir, by
Yes.
changing the position of H and
Yes.
Y.
Yes. Exactly. If we change the position of any two groups attached to the central carbon atom, and if it is generating a new stereoisomer, then we will call this center as the stereogenic center, right?
Yes, sir.
Like in this molecule, suppose we change the position of this carboxylic acid group and the methyl group, then we will get a new stereoisomer, right? So this center is called the stereogenic center. Okay, let's discuss it with a elaborate example, then it will be very much clear. Okay, let me draw one molecule. Okay, so in this molecule, how many chiral centers are there? Hello,
So two.
why two? Which one?
So 3 carbon.
Three. Three chiral centers are there, na? First is this one, second is this one, third is this one, right? This is the C2. If we start with this is the 1, this is 2, this is C3, this is C4, and this is C5. Okay, so we will check
So,
whether, sorry,
sir, sorry to interrupt. Sir, I didn't get like how can we say that C3 carbon is a chiral carbon?
uh, why not?
So, like if we will look the substituents of C3, so the C2 substituent and C4 substituent appears
Mhm.
same, right?
These are same, but optical rotation or the descriptors are different, na? This is the connectivity is same. The same is connected here. That is hydrogen carboxy group and OH. This is OH carboxy group and the hydrogen. But if we denote it as the R or the S, then we will see that one is R and the another is S.
Okay, sir.
Okay. Sorry, the this may be same R or S, but there is no mirror plane right here, na? So if we consider, we will check it. We will come with this center by center, then we will see what is whether it is chirotopic or stereogenic. Okay, so now let's first come to the C2, whether it is chirotopic or not. Does it has any plane of the symmetry here at the C2?
No, sir.
then it definitely resides in the chiral environment, so it is chirotopic. Is it stereogenic? How we can designate whether it is stereogenic or not? If we change the position of the hydrogen and the OH mutually exclusive, then OH will come this side and hydrogen will come this side, then it will generate a new stereoisomer, right? The all OH groups will come this side and the all hydrogen will come this side, so it is stereogenic center, right? Now come to the C4. This is the same as the C2. If we it does not contain any mirror plane over here, so definitely it is chirotopic and stereogenic also. And what about C3? Does it contain any kind of mirror plane?
No, sir.
No. And you were saying that how C3 is the chirotopic, the bonding, the two groups are the same.
Yes, sir.
Yes. So suppose if a imaginary mirror plane, if we keep here, so is this perfectly reflecting the groups through this atom? See the hydrogen in the C2 in this side and hydrogen in the C4 at this side. So it is making two halves of the equal of the molecule, that mirror plane.
No, sir.
No, na. This is why we will call it chirotopic. If in this molecule the OH would come here, then we will call it achirotopic. Then it will, like in case of this molecule, if all hydrogen is this side and OH is this side, then at a mirror plane is present over the here, and it is perfectly the reflecting the first half of the molecule and the second half, then we will consider this center as the achirotopic. Okay, is it clear?
Yes, sir.
Yes, sir.
Okay, so now tell me the last one, that whether C3 is stereogenic or not. This center is stereogenic. If we change this hydrogen here and OH here, does it generate a new molecule, new stereoisomer?
Yes, sir.
No. Think deeply. If we change the position of these two groups, okay, so here hydrogen, then after changing, hydrogen will come here. Okay, this is our new molecule, right? Hello.
Yeah, yes, sir.
Then you give a 180-degree rotation of this molecule in the plane of paper, then it will look exactly same like this. Okay, so you just bring this upward carbon downward, this the down carbon upward, then these two OH group will come here and it will be the same molecule where we started. So it is not generating a new stereoisomer, that is the C3 is non-stereogenic center. Okay, so I am just explain this to make you understand that stereo chirotopicity and the stereogenicity are not always the same term. Though the C3, this carbon is chirotopic, but this is not stereogenic center. Okay, you got it.
Yes, sir.
Okay, any doubt, anybody?
Sir, can we assign the RS nomenclature at C3?
Yes, we can. Huh?
Sir, C2 and C4 has same configuration R. So how can we prioritize while naming at C3?
Okay, these are same. Have you done? We checked this.
Yes, sir, I have checked. C2 and C4 has same configuration.
Okay. Okay. Same configuration. Okay, then we cannot assign this as a R or S nomenclature.
Sir, C3 is a non-stereogenic center. That's why we are not able to
Not able to
assign.
assign this. Okay, let's move to the next question. So, shown below is the chemical structure of the penicillin, a common prescribed drug. How many chiral carbons does penicillin have? So, now tell me, it is very easy. How many chiral carbon? The chirality, how can we measure the chirality?
Four different groups should be attached to
Uh,
a carbon.
Four different groups should be attached to the carbon. So now tell me what is the right answer? How many such chiral centers are present here?
So three.
Three.
Three. The first one is this one, right? Second one, this one, and third one, this one.
No, sir.
No, sir, below it.
Why? Tell me why not or why?
So that particular carbon have two methyl group.
Yes, these two are same group. So we you cannot say this center as the chiral center, right? So the third one is this one. So one, two, and three, right?
Yes, sir.
Okay. Okay. So now what is saying here? When an agonist binds to a receptor for a long period of time, it can result in a phosphorylation reaction occurring. Which of the following term is the most relevant description of the immediate effect? So now tell me what is the right answer when an agonist binds to the receptor for a long period of time, which is the result immediate effect of this incident. What we will call it? We will call it a tolerance or dependence or sensitization or desensitization. Anybody?
Desensitization.
How? Why? What is happens there when a agonist binds for a longer period of time? What are the process begins at that particular position? Okay, let's discuss it. Okay, yes, you are absolutely right. This is desensitization. When an agonist binds to a receptor, it causes a induced fit which result in the receptor adopting an active conformation. Okay, this is the induced fit mechanism, right? If the agonist binds for a longer period, phosphorylation may occur, which causes the receptor to change shape into an inactive conformation. In other words, the receptor becomes desensitized to the agonist. So, what we are saying that when agonist is binds to a receptor for a longer period of time, then phosphorylation takes place, and this the what is the action of the agonist? It changes the active site of the receptor, but when it is occupied for a longer period of time, then some phosphorylation reaction takes place, and it changes the active site of the receptor as it cannot work like the previous one. Okay, so the right answer is desensitization. So now what is tolerance? The other terms present here. Tolerance is a situation where increased dose level of a drug are required to produce the same effect, which dependence is related to the body's ability to adapt the presence of a drug. So, when the receptor is tolerant with the present drug, then higher concentration, increased dose is required. That is called the tolerance. Okay. So, the tolerance is a decrease in the response to a drug that is used repeatedly. Okay. So, this is called the tolerance. And our right option is the desensitization. Okay, so what is the structure of the compound is shown below, which structure is different from the following. So what is the name of this ring? What we call it? What is the common name of this ring? What we call it?
So cyclohexane.
Cyclohexane, yes. And what is the most stable form of the cyclohexane?
Chair form.
Chair.
Chair form. Because of the some strain, it adopts itself in a Packard, this chair form, that the non-bonding interaction with the adjacent carbon atoms is minimum here in the chair form, right? So let's now see which is the not which is different from the other. So if we convert it to the normal convert, here it is in the upward direction, right? This CH3 is above the plane, so we will call CH3 here, and here CH3 is also above the plane. Okay, so we will draw only the 2 1 3 part, and the adjacent one, that is the down the plane here. Here CH3 down the plane, here above the plane, and here also above the plane. In this case, Wherever the plane. Put a document here. Put a plane. So, which is different from the other structures? Can you convert that how to draw that this above the plane to the this chair form, or shall I describe that how we should draw it? You got it that how it can be converted to the normal cyclohexane from the chair form to the normal form by drawing. Hello, hello,
Yes, sir.
hello. So can you follow it that how it is being drawn from the chair form to the normal ring form? That as
Yes, sir.
the CH3 group is upward direction in the chair form, so I put it in the above the plane form. This the rigid bond, and here the CH3 group is down the below the plane, so I drawn it in the that dotted line. That's to show that CH3 is below the plane. So now tell me that which one is different from the other structures.
Second one.
Second one, why? Why it is different? Why it is different?
Because, sir, in other structures, two methyl group are on upward and one is downward.
Hmm.
But in second one, two methyl group are downward and one methyl group is upward. It is different from
Exactly.
the given in question.
Absolutely right you are. That in given question we are given there that it 1 3 position, that two methyl groups are upward direction, and adjacent to that one methyl group is below the position. So in the other structure, that is 1 3 and the 4, we have seen that the two methyl groups are at 1 3 positions are upward direction, and the adjacent one methyl group is below the plane. And only in case of the second structure, the 1 3 position, one is upward, one is downward, and the adjacent one is below the plane. So this one is the odd one out. This structure is different from the all three one. So the right answer is option B. Okay. Any doubt, anybody? Or we will move to our next question. Okay. So what is being asked here, that what sort of agent binds to a binding site that is next to the binding site for an endogenous chemical messenger that sterically blocks the messenger from binding. So it is saying that a chemically agent uh, that binds to the just next to its binding site and sterically blocks the messenger from binding. What we will call it? So it is sterically blocks the messenger from binding. So it is blocking the active site. So definitely it is agonist or antagonist.
Antagonist.
Definitely it is antagonist. So the first option is ruled out here, that the first option is agonist. It cannot be an agonist, right? So inverse agonist, it is not an agonist. So the two option is left here, that allosteric antagonist or an antagonist acting by the umbrella effect. So which one? It is a allosteric effect or umbrella effect. So allosteric effect I discussed in the last session. What is allosteric effect? Anybody wants to say what is allosteric effect? Okay, I am explaining in very short. See, suppose this is our structure of the enzyme, and here this is the substrate. This site is called the allosteric site, and support this molecule act here. One molecule, this is the active site, and this is the allosteric site. Suppose this molecule binds here, and after binding this molecule, the active site of this enzyme is changed like this way. Okay, this is allosteric site and this is active site. So this is the substrate. So it cannot bind to the substrate directly as a compound which is bind to the allosteric site and change the conformation of the active site like this way. It cannot bind to its substrate directly. So this is called the allosteric inhibition. Okay, have you got it?
Yes, sir.
Okay, so now tell me, is this allosteric inhibition in this question? That a binding site, what sort of the agent binds to the binding site next to the binding site for an endogenous chemical messenger that is sterically blocks? Is here it is binding sterically in the allosteric inhibition? No, this is not binding or inhibiting the sterical interaction. It is attaching to a different site and changing the conformation in such a way that the substrate cannot bind to the active site of the enzyme. So this is not steric interaction at all. So now let's discuss what is the right option. An agonist bind in the same way as the natural messenger and activates the receptor. Okay, we discussed in our first question. Somebody told me very right way that it agonist in the same way like the endogenous messenger does. An allosteric antagonist bind to a different binding site, as I discussed already, that it binds to the different binding site, but resulting induced fit distort the binding site for a chemical messenger such that the later one is no longer recognized. It changes the active site of that enzyme in such a way that the substrate molecule cannot fit it in this position in the active site of the enzyme. The umbrella effect occurs when an antagonist binds to a site next to the normal binding site and part of the molecule overlaps the normal binding site such that it acts as a steric shield. Right? So, suppose this one is the enzyme, and at this position a big molecule binds in such a way that it hinders the active site of the enzyme, so that a real substrate cannot come closer to this active site. Can you get it? Here the steric mechanism coming to the place, that due to the steric bulk of this particular molecule, which is binding just in the near proximity of the enzyme, the substrate molecule cannot come closer to the active site of the enzyme. This effect we are calling it as the umbrella effect. Everybody got it?
Yes, sir.
Everybody understood that how it is different for the allosteric inhibition? And now an inverse agonist binds to the receptor and stabilizes an inactive conformation such that the natural messenger cannot bind. Furthermore, any inherent activity is lost. Such activity is associated with the low levels of the active forms of the receptor. These are present despite the absence of an endogenous messenger, but equilibrate to inactivate conformations in the presence of the inverse agonist. So this is the case of the inverse agonist. Just for information I have put here. So it is clear what is umbrella effect, that the sterically blocks the messenger from binding. This is suppose messenger and this is the active site. So the due to its bulkness or the steric hindrance of this molecule, it blocks from the binding to the active site. So this is clear. Then we will move to our next problem. Shall we move to the next question? Nobody is responding. Okay, let's move to our next question. Okay, so this is very easy. We have discussed this earlier, that what process takes place to produce desensitization of a receptor when agonist. We have already, it was there in the question. So what is the right answer? Esterification, phosphorylation, peptide formation, or peptide hydrolysis? Which one? It was there in the question already.
Phosphorylation.
Phosphorylation. So desensitization, we have already discussed that when an agonist molecule keeps bonded for a very long time uh, to the active site of a receptor, then due to the phosphorylation, the desensitization takes place, and the process through which it occurs is the phosphorylation. Right? Okay, so next move to the our next question. Now we have to match here, that identify an amino acid in an active site whose residues could bind a drug principally by. So we have to identify which uh, amino acid binds to the receptor, active site of the receptor, by the effect, which effect. So now first option given here, it is serine. So what is the active part in the serine? In the side chain there is a OH group is present in the serine, right? So now aspartic acid is there. So from the name itself, it is very clear that In side chain, a carboxy group is present there, and then it is coming as the valine. Valine, there is no polar group is there, only a hydrophobic side chain is there in the valine. And then glycine. Now tell me the structure of glycine. This is the simplest amino acid. You have to tell me the structure of glycine. This is common structure. Now what is there in this carbon? In glycine, what side chain is present there?
Hydrogen.
Hydrogen, yes. So this is the simplest amino acid, glycine. So now tell me which is possible for the conformation. Four options are there. Hydrogen bonding is there, ionic bonding is there, van der Waal interaction is there. So now tell me for among this structure, who can form the best hydrogen bond uh, depending on the side chain present here. Glycine can form hydrogen bonds.
No, sir.
Why not? Because it doesn't have any functional group right here to form the bond, right? Right?
Yes, sir.
Can valine form the hydrogen bond with this hydrophobic isopropyl side chain? As we know that to form a hydrogen bond, that the molecule, the atom has to be electronegative, right? So the hydrogen has to bonded to electronegative atom, and another small electronegative atom is should be present to form a hydrogen bond in between. So the what is the best possible structure to form hydrogen bond among these four? I have already shown here that who can form the best hydrogen bond with its neighboring groups.
Serine.
Serine. Yes, due to the presence of the this OH group, O oxygen and hydrogen. Hydrogen is bonded to electronegative oxygen, so it can form a strong hydrogen bond with its neighboring group. So hydrogen bonding gone with the serine. Now ionic bonding. Who can form the ionic bond? Which side group can be ionized? Can isopropyl group be ionized at physiological condition? Or glycine can be ionized? No, only the possible option present here. Thus, the carboxyl acid group is present here in the aspartic acid, so it can easily form the hydrogen ion. So it will form as the it will remain as the this one. So as this is the ionic compound, carboxy group, so it can form ionic bond with its neighboring ion group present here. So ionic bonding gone with the aspartic acid. And then the last two options, that van der Waal interactions and none of the above. So which one go with van der Waal interaction? Non van der Waals, non-bonding interaction. Who will form valine or glycine?
Valine.
Valine. Due to the presence of the this hydrophobic group, it can form a van der Waal interaction with its neighboring some hydrophobic group or atoms. Okay, it can form non-bonding non-bonding van der Waal interaction. So valine will form van der Waal interaction, and due to absence of the any functional group in this carbon atom, so none of the interactions is possible for the glycine. So the option 1 is the right one, that hydrogen bonding will go with the serine, ionic bonding with the aspartic acid, van der Waal interaction with valine, and none of the above with the glycine. Okay, it is clear. Then we will move to our next question.
Sir, van der Waal interaction is the weakest interaction. Every molecule can show this kind of interaction, sir. So glycine can also show, sir.
Yes, glycine can show, definitely it can show, but when there is some hydrophobic group is there, na, then it is better. Then it is a hydrophobic pocket is there, na, only isopropyl group is there, 3 carbon atom, that only hydrocarbon chain with no functionality is there. So it can show a better bonding with the another hydrophobic part of a molecule. As we are comparing here with this can definitely show some sort of, but it can show better way. Okay, due to the presence of this isopropyl group in valine.
Yes, sir.
Okay, here isopropyl, like a leucine is present there, that four carbon atom group. Then with this isopropyl group and butyl group, there will be a better interaction rather than CH2 group with this butyl group. In this way, we are saying that valine is able to form a better hydrogen wall interaction with its neighboring groups. Okay,
Yes, sir.
so we will move to our next question. Okay, did you get the structure that it is written in there, that which is the correct assignment? But I did not find any structure in this question. Did you find any structure?
No, sir.
Yes, this is the problem. I searched it, but it did not show any kind of structure there. And answer is also given. I don't know how it comes. Okay, so we cannot assign this structure. We will discuss this last question of our today's session. That somebody asked me in the earlier class, that how can we differentiate that which is competitive inhibitor, non-competitive inhibitor, and uncompetitive inhibitor. So today we will discuss with respect to this question. Okay, so now tell me what is the right option here. What type of plot can be used? Just a second. What type of plot can be used to determine whether an enzyme inhibitor is competitive or non-competitive? Can we plot it from the Michaelis-Menten? Can we? Okay, so let's come to the right answer. This is the, which one is the right answer?
LB plot.
LB plot. Yes. From this one, we will discuss how we can determine what kind of inhibition is present here. Okay, so please follow. So when inhibitor interacts with an enzyme, it decreases enzyme catalytic activity, right? So this is definite. If an inhibitor binds with the enzyme, then it definitely decreases its enzymatic activity. So an irreversible inhibitor uh, binds with the active site covalently, produce permanent damage in efficiency even we decrease the inhibitor concentration. So what is irreversible inhibition? Then this bonding is the covalent one. Is it permanently get bonded to the enzyme moiety, and even we decrease the inhibitor concentration, then also this inhibition takes place, means this is irreversible one. And what is then reversible inhibition? Reversible inhibitor forms non-covalent complex with the enzyme, resulting a temporary decrease in the catalytic activity. That in case of reversible, it forms some weak bonding interaction with inhibitor and the enzyme, that even if we decrease the inhibitor concentration, then against this activity of the enzyme can be restored. Okay. Is this clear what is reversible inhibitor and what is irreversible inhibition? Hello.
Yes, sir.
Okay, so there are various pathways present for the reversible binding of an inhibition. Reversible binding, what we discussed in our this reversible one, that is the weak bonding interaction is there. So there is some three different kind of mechanism is present there. One is the first one is what? Competitive inhibition. So here an enzyme and substrate is present. So okay, so let me draw in fresh book. Some enzyme and substrate is present there, and it is forming an enzyme substrate complex, and it is giving as the enzyme plus product. So now in case of the competitive inhibition, this inhibitor competes with the substrate and forms the EI complex. So the next one is the non-competitive. In non-competitive inhibition, the first part is same. It can form and the third one is uncompetitive. In uncompetitive, it doesn't make any kind of competition with the substrate molecule. Okay, so these are three different schematic for the reversible inhibitor molecule. First one is the competitive, that it competes with the substrate molecule. The third one is non-competitive. Even we can see that after the binding with the substrate, enzyme substrate, it can form that ESI. ESI means enzyme substrate and inhibitor complex. Okay, so it can form this complex, and third one is the uncompetitive inhibitor. So They are three different nature we can determine from the EB plot. So how does they look? Let's see. So we can identify the type of inhibition by observing how a change in the inhibitor concentration affects the relationship between the rate of reaction and substrate concentration. We can display the kinetic data using LP Bark plot. Okay, so the three different kind of graphs will looks differently in this plot. Okay, so here we will 1 by substrate, this is 1 by rate. So in case of the competitive inhibition, okay, so in case here in the first one, this is the thicker line is I equals to 0, this line, and in this direction concentration of inhibitor is increasing. That is, this is the higher concentration and this is the lower concentration. This is in case of the competitive inhibition, and this in case of the non-competitive, it will somewhat look like this way. Like the same way, the thicker line, which I am making a thicker one, here concentration of inhibition is 0, and this way, this direction, the concentration of the inhibitor is increasing. This is the graph in case of the non-competitor, and this is case of the uncompetitive one. Let's start from this one. It will not at all cross each other. Okay, so this is the three different kind of graphs and we get in the LB plot when we plot the concentration of the substrate with the rate of the reaction. Okay, reaction rate and substrate concentration. Somebody asked me in the last question, so it is the clear cut answer that how we can differentiate between the competitive inhibition, non-competitive inhibition, and uncompetitive inhibition. So in this way, we can say that see that the y-intercept is same in case of the all three cases, and as the concentration of the inhibitor is increasing, we are getting a higher slope here. Here the y-intercepts are different in all the cases, and the slopes are getting increased. And here the two slopes are also slopes are the same, but the intercepts are increasing with the increase in the inhibitor concentration. Okay, so in this way LB plot we can differentiate between the three different reversible mechanism: competitive, non-competitive, and uncompetitive one. So unfortunately, in our last question, we are not able to see the correct structure, so we could not discuss about it. So apart from this, anybody has any doubt regarding this? So he or she can raise the problem. So is this clear to everybody?
Okay, sir.
So nobody have any doubt, right?
Okay, sir, but I want to ask one question.
Hmm.
What is the passing criteria? I mean, how the evaluation takes place?
I think the official website will guide you better in this respect. Means the what is the passing criteria and about the exam pattern. I think better you ask any help desk or any number is given there. Means
Okay, okay.
okay.
Thank you.
So any subject
Okay,
related doubt you can ask me. I can help you in this regard.
okay. Thank you, sir.
Okay, so if nobody having any doubt, then we will end up our session here and we will meet in the next session. So,
Okay, thank you,
okay,
sir.
thank you for joining. Thank you.
Thank
We
you.
will meet on the next class.